Is representing multiple layers that you are representing in the model, not the actual measured data. So just a few points to note. The layer numbering scheme in SEDZLJ, layer 1 is the top layer. Layer 2 going down. Layer KB, the maximum number of layers that you're going to specify is at the bottom. So 1 to maximum number of layers. The layer 1 is, we'll talk about it more later, but it is literally the active layer. It is constantly changing thickness based on applied shear stress. And depending upon as it changes thickness, it's either taking material from layer 2, if there's material in layer 2, or from the next active layer below. So it's exchanging material between those two layers as the active layer is changing every time step with the applied shear stress. But important to note is that layers 1 and 2 should not be initialized with any sediment. They are specifically used within the computational framework of EFDC. So actually, we'll talk about it a little bit more, but I'll just show you what we have on the form here. So here on the form, we've got active layer 1. It says active, but it's really, that's the depositional layer. But these two layers here should always be initialized with the 0 thickness, because they're actually predominantly results from the actual computational process. And we'll describe it more later. There is some capabilities in EFDC Plus and SEDZLJ. So like you can specify regions of the model or a cell of the model that actually has no sediment initially. That doesn't cause the model to crash. So you can essentially like it's on bedrock. And so there's no sediment there to erode, but however, that sediment may deposit during the simulation. Not a problem. So that's a implementation issue within EFDC Plus. The other thing, just as you're defining your layers, this is actually a little bit of an upgrade that I need to make in the code that's not quite there yet. But let's talk about empty layers. Let's say you have 10 layers defined in your model. The first 2 are your active layer, and then what they call the deposition layer, and again we'll talk more about it. But this layer, if this cell is continuously being is receiving deposition from your upstream cells, the way the SEDZLJ model works is it takes this sediment as it's coming, settles onto the active layer. It calculates how thick that active layer should be, and any sediment that's in excess of the thickness of the layer gets added to your deposition layer. And right now, that deposition layer has no limit. It just keeps growing and growing and growing, or shrinking if you're eroding after you had deposition. But this deposition layer could potentially be 10 meters thick. The problem with that is that actually has bigger impact maybe on the toxics transport side, because the material coming in may not be uniform. Sometimes it might be more contaminated than others, depending upon the dynamics of what's going on in your system. So that's probably 8.4, we're going to start adding the ability to limit the maximum layer thickness. So as you get to the point where you're depositing, and then you hit that limit, it will take that sediment and add it to a uninitialized layer below your deposition layer. So that way you can get discrete grain size distributions and discrete toxic profiles in your deposition layer. But the model right now just lumps it, your deposition, all deposition ends up in this deposition layer here. But the empty layer concept here is within the EFTC plus framework right now, you can still have, let's say you've got 10 layers and you initialize the model layers 6 through 10. So layers initially, layers 1 through 5 have nothing in them. You turn on the model, model's running, you have erosion, you've got deposition processes going on. All of a sudden, you have layers 1 and 2 have data or have sediment in it. Layers 3, 4, and 5 are still empty. And layer 6 is down here as kind of a parent layer providing sediment if it needs it up into the water, up into the upper layer, bed layers. Within the computational framework of EFTC Plus, that's not a problem. And the reason why we've kind of configured it that way is so that we can add multiple layers once the depth, so we can hit this maximum and start filling these empty layers below. That's the concept of why we constructed it. It's just not quite there yet as far as the implementation. Any questions on this layering scheme? Okay. So let's just look at some of the major processes in SEDZLJ. So again, you've got your water column here. Your velocity profile, you have this layer thickness, a bed load layer thickness represented here. Now, you see that this E represents the erosion that is from your measured SED flume data. So I know initially, based on the applied shear stress at this boundary, I know how much sediment is coming off of the bed. But that is only at this interface here. So I have an E total, but not broken into the suspended load fraction and the bed load fraction. So SEDZLJ has a process where it divides how much of that sediment that's getting eroded, how much of it just rolls along the bottom or saltates and hops along the bottom in bed load, or how much of it actually makes it up into the water column. And we'll talk about that function later. So that process is being simulated. Then you have a bed load, again, it's optional, a bed load layer that gets established based, again, on shear stress and grain size. And then you have a movement of your bed load. So it gets suspended. So no, it's no longer part of the mass in the sediment bed. It's not in the water column, but it starts moving along the bottom as a hopping, rolling condition. That is reflected up in a velocity term called the UBL, or the velocity of the bed load in the X and the Y. So that process is being simulated in SEDZLJ, and that's unique. And then again, on the depositional side, you have the material that's in bed load. It may need to deposit because the shear stresses are dropping, because it rolled into a different cell and your dynamics are different, or whatever reason. You have to calculate the deposition from the bed load layer into the top, into your active layer. Now, you also have suspended sediment in the water column. Now we're counting essentially, that's the mass of sediment and everything essentially above your bed load layer, but it actually includes your bed load layer as far as the, if you're calculating the actual mass. But all of, if that material deposits, whatever material deposits, it deposits completely through the bed load layer and into the active layer. There's no splitting of that deposition from your water column, some of it going into the bed, some of it kind of adding to the bed load. It just goes straight into the active layer. And then we talked about, I just mentioned it before, but then if there ends up with excess material in the active layer based on how thick it should be, based on your applied shear stress at that time, it bumps that material down into your deposition layer. Likewise, when you're eroding, as your active layer starts losing mass, it needs mass because it has to keep that thickness, because that thickness is defined not by your bed, but by your hydrodynamic processes going on. So it borrows or takes sediment from the bed below. So it keeps that thickness of your active layer appropriately sized for the shear stress that's being applied. Now, I mentioned this briefly before, but shear stress, there's a couple of different kinds of shear stress, and the hydrodynamic model needs a bottom shear stress for the solution of the hydrodynamics to get the velocity profiles, and it calculates an internal hydrodynamic shear stress, and that shear stress is what was originally, what by default is used in the EFDC code. However, the original code then later added some options for actually calculating a grain size or skin friction shear stress from the hydrodynamic stress. SEDZLJ basically totally bypasses that whole process. And then in the EFDC Plus code, basically we just have whole blocks of the sediment transport code commented, or not commented out, bypassed with a logical block. So if you're doing SEDZLJ, we just skip to a different section of code, and this is how the SEDZLJ model calculates bed shear stress based on, down here you can see the D50 or this ZB is not your hydrodynamic roughness factor, it's your grain size roughness factor. So here it calculates based on the total depth of water, von Karman's, and calculates a drag coefficient, your friction factor, between the water at the current velocity and current depth and your grain size, and then that goes up here into your velocity term and your skin friction factor to calculate your grain size specific shear stress. So this is how EFDC Plus calculates shear stress. Now, this is, we've modified the documentation to be clear about this. There is a if statement inside of all SEDZLJ models I've ever looked at that says if your water depth is below a certain size or a certain depth, it's going to apply a 0 value for the friction factor, so your bed shear stress goes to 0. And it was hard-coded in the original model at a ½ meter. So if your water depths ever drop below a ½ meter, you'd get 0 shear stress. That's now an optional parameter in EFDC. And obviously you need to have some kind of limit because you're dividing by depth. Of course, if it ever goes to 0 or quote-unquote dry, you know, it would, the model should be, if you have wetting and drying, it should be turned off. But anyways, all that to say that it just limits it. And if you're using an earlier version of the model, just be aware that this may be hardwired to 0.5 meters. So, erosion. Kind of a process that needs to be understood is that you have measured data for your in-place initial conditions sediment profile. So I know I have a core, I know I have erosion and critical shear stress and densities and grain size distribution measured for that in-place sediment. But turn on the model, this stuff starts getting eroded, it gets moved. What happens to the deposited material and the material that has been essentially removed from the your native material and now is in this active layer? And so there is two lookup tables you'll see in the data set, and the model uses these. You use one for calculating erosion rates for your measured data for all your layers greater than 2. And if we end up adding this depositional layer ability, we'll have to end up with a flag that knows that this layer is a depositional source or is it the original data. But nonetheless, you essentially where you have measured data in undisturbed layers, it uses the measured data when it's calculating erosion. If, however, you have an active and deposited layer, layers 1 and 2, it uses a different lookup table and different shear stresses that you have to define in the input data set. They're not course specific. They're uniform across the system, but they're by grain size distribution. So once you have that defined, it'll apply that same approach for the entire model domain. Yeah, and so you're having to estimate this, what they call active and deposited sediment erosion rates, critical shear stress, etc. And you just do that from the data. Maybe all you need to do is just take some of your top layer data and either pick a representative core and say that applies elsewhere, or you average it, or however you want to do it, but you end up having to estimate this. Earl, any advice